Today we're going to be going over momentum. And make sure you copy this on the left side of your notes. Here is well, you can copy this part right here on the right side. Just this little part right here. Because that's the formula. So what is momentum? Well, you want to picture momentum. Well, let's look at the formula. Okay. So it has P equals mv. So P stands for momentum. Why did they not use m for momentum? Because m is already mass. So here we have mass times velocity. So picture momentum like if you're trying to stop something that's moving, how much effort or force do you need to kind of put to be able to stop that? So that's kind of a way you want to describe or see momentum. Momentum is how fast something is going and how heavy it is. So you can have something that's really big and heavy, like let's say a car that's parked up on a hill, and let's say the brakes go out and you're trying to hold the car from rolling down the hill. Okay, it's gonna have a big momentum, right? As once it starts rolling, because it's very heavy, right? It might not be moving that fast, but it's very heavy. Or you might have something very tiny like a bullet that's moving very fast, but the mass is very tiny, right? That can have a big momentum, right? So there you go. That's kind of on a nutshell of what momentum is in a way. So here are the units. Momentum is in kilograms, velocity is meters per second, and the units for momentum are kilogram times meters per second. Okay, so if we look at the first example here, a compact car with a mass of 725 kilograms is moving at 115 meters per second. What is its momentum? So let's figure out where these go. So here we have 725 kilograms that goes in mass. And they're giving us the velocity, right? Meters per second, that's velocity. So what are we going to do with these two numbers? Yes, you guessed it, multiply. 725 times 115, and that gives me a momentum of 83,375. And the units kilograms times meters per second. Okay. Now if we go to the second example, a 7 kilogram object is moving 2 meters per second. What is its momentum? Well, again, they're giving us the mass, 7 kilograms. They're giving us the velocity, 2. 7 times 2, 14 kilograms times meters, meters per second. Okay. Let's go to the next example. So this is going to be, well, it's going to be a little bit, not harder, but here, let's copy this on the right side. Let's do this. Right side of your notes. So you're going to find the momentum of a 3,000 pound car traveling at 10 miles per hour. Now, if we ever needed to convert stuff, like 3,000 pounds, we need to convert it to kilograms. Now, the problems that I'm going to give you should not be this difficult. I think I'm just going to give you kilograms and all that stuff. But if you ever encounter something like this, where you have to convert pounds to kilograms, well, 3,000 pounds there's 2.2 pounds and 1 kilogram. So we're actually dividing these two numbers, 3,000 divided by 2.2. 3,000 divided by 2.2. And that gives me 1,363. Another trick you could do is, here, let's try it. On some of these problems that I might give you, you could maybe even just go in Google and just put convert pounds to kilograms if you don't want to go this route, and it'll give you, it's somewhat close, okay? 1360, we put 1363. But that's kilograms. Your answer has to be, your mass has to be in kilograms. And let's convert 10 miles per hour to meters per second. Okay, so I'm going to come over here. So 10 miles per hour. So I kind of give you here that in miles, in 1 mile, there's 1609 meters. And we need to convert hours. So miles is going to cancel here. So we're left with meters. We want the bottom to say seconds. So hour is going to jump up. And we know that in 1 hour, 1 hour, there's 3,600 seconds. Okay. So when I do 10 times 1609, I'm going to multiply everything on the top. I get 16,090. And I'm going to divide that by 3,600. And that gives me 4.4 meters per second. Okay. I know this problem is a little odd. It's they're not giving you the stuff right away, but this is just in case if they want to, if they give you something like this, we want our answers to be in kilograms and meters per second. So these are the numbers that we're going to be using. So this is my mass, and this is my velocity. So my mass times my velocity, right? So that's the formula, meters, mass times velocity. So 1363 times 4.4 gives me 5,997 kilograms times meters per second. Okay. I'm aware again that this was a little odd problem. Not all the problems that I give you are you're gonna have to do conversions. So let's look at another example. I'm gonna erase this. Okay, so it's not, the bottom one is, well, it's kind of the same, right? 4.2 grams. That's actually this many kilograms. And if you go on Google as well, here, let's see if it's in there. Convert grams to kilograms. So 4.2. There you go. It's exactly what I put, right? Now the trick for that is you kind of have to learn how to go from grams to milligrams and all that stuff. So here we have grams, and to go to kilograms, you just move the decimal 3 times to the left. Okay, but that's besides the point. So 1,700 miles per hour. I'm going to convert that to meters per second. Miles per hour. And we know that there's, in 1 mile, there's 1609 meters. And in 1 hour, there's 3,600 seconds. Okay, so I'm going to multiply everything here on the top, 1,700 times 1609. And that gives me 2,735, 300. And we're going to divide that by 3,600. Divided by 3,600, 759. Oh, wait a second. This is the velocity, so that's not the answer. $759. Meters per second. Okay, so now we're going to do mass times velocity, right? The mass times the velocity gives me 3.1. Kilogram, 3.1 kilograms times meters per second. Okay, now we're going to jump to conservation of momentum. So this is on the right side. So here, the conservation of momentum is, let's say you have a little picture, or let's say you're running, and you are running, right? You have a mass, you have a velocity, and you jump on a skateboard. The skateboard also has a mass, right? It weighs something. The velocity is 0, it's not moving. But once you start running and you jump on the skateboard, you're both going to be moving now, right? Where before the skateboard wasn't moving, now you're going to start moving because you ran and you jumped on it, and now you're both moving, right? So that's what this formula kind of explains. So here you have the mass and the velocity of the guy or girl running, the mass and the velocity of the skateboard, and once this person jumps on it, now you have the person and the skateboard, right? Mass 1, mass 2, and now you are both moving. Okay, so this is the formula that we're going to be using. So this is there's two types of equations. There's elastic and inelastic equations or collisions. Okay, so I'm going to go more deeper into this with the other slides, but in elastic collisions, some kinetic energy, so kinetic energy is energy that's moving, right? You have the guy that's moving. Some kinetic energy is lost when it is converted into another form of energy, such as heat, light, sound, so on. You also have elastic collisions, and this is no energy is converted into heat during the collision. So kinetic energy before and after the collision remain constant. So the best way to see this is with this next slide. Okay, so here we have our first example. So that's going to be on the left side. So here you have two freight cars. These are let's say they're like on the train tracks, right? These two big heavy freight cars. Okay, so there's one on the tracks, and there's another one on the track, right? They both have the same mass. So if this one has this mass, then anything that has an m, we're just going to plug in that same mass to everything. Okay. Don't get confused. All I did is, if it says an m, I just plugged in that number because it says that the weight of that car, it's the same for all of them. Therefore, all of the m's are going to have the same, okay, number. So two cars, there's two cars, and let's say this one is moving and this one isn't. Okay, so how fast is this one moving? Well, one was initially moving at 2.2 meters. So we know the velocity of this one was 2.2 meters. And the other is at rest. So this one's not moving, 0. So when they crash, let's say here you have a crash, right? Now that they crashed, they are both going to be moving, right? They both crashed. Now they're both going to be moving. So how fast are they moving now, right? If this guy was moving at 2.2, it crashed into one that's not moving. Now they're both going to be moving, but how fast are they going? Okay, so that's V both. Okay, so now we're going to multiply, and I have gone over how to multiply exponents. Okay, so notice this one right here, this has an exponent times 10 to the 5th, and this one doesn't. So the easiest way to do this is you're going to just multiply 3 times 2.2. Let's do that. 3 times 2.2. And that gives me 6.6. This guy right here did not have an exponent, so you can just leave it as is. Okay. Now I want you to notice in this equation right here, m1 is 3 times 10 to the 5th, v2 is 0. So here we're going to multiply this times 0, and we know that that is 0. Okay, so we don't have to do anything there. Now here m1, m2, m1, m2, we're going to add these. Now the rules for adding exponents, these guys here have to be the same. If they're not the same, you have to make them the same by moving decimals around. But they're the same, we looked out. Therefore, we can just bring that down. Okay. So now I'm going to add, it's not telling me to add, 3 plus 3 is 6. Okay. Okay, so now we want to solve for the velocity. So we want v to be by itself. So this whole thing, we're going to move it. We're going to move it to the left. This cancels. We're left with v both. So now we are going to divide this right here. 6.6 divided by 6. I think that ends up being 1.1, right? Oops. 6.6 divided by 6 is 1.1. Now I want you to notice also, what do you do with exponents when you are dividing? You're going to subtract them, right? 5 minus 5 is 0. So this is our answer. Okay. And there we go. That's our answer. Okay. Now, let me go to the next example. So make sure you copy this on the left side. So here you have a hockey player or a hockey puck. Let's say this is the hockey puck, and it's moving at 24 meters per second, and it's caught by a goalie. So here you have the goalie. He's going to catch it, right? So once the hockey puck hits him, he's going to probably move back, right? The momentum of this is probably going to move him back, maybe not that much since it's a tiny hockey puck. Maybe if it was something bigger, it would move him back. But let's see how far it moved him. So we know that the hockey puck has a mass of 105 kilograms. And we know the goalie has a mass of 75. So here M1 we know is 0.105. And M2 right here is 75. Okay. Now this said that the hockey puck was moving 24 meters. This is a hockey puck, so we're going to plug that velocity in. And the velocity of the goalie is at rest, so he's not moving. So now we want to find out, well, once the puck hits him, here he's going to catch it, right? It's going to be him, which is M2, and he catches the puck. It's going to move him back, okay? But how fast? Probably not that fast, but let's find out. So we have all the numbers set up. So let's break it down. 0.105 times 24. 0.105 times 24 gives me 2.52. This is nice, right? 75 times 0 is 0. This is nice too. 0.105 plus 75 is 75.105, right? When you add both of them. So now we want to solve for v by dividing. This cancels, and we're left with 2.52 divided by 75.105. And that gives me 0.03. And notice this was almost nothing, right? Obviously, I mean, it was just a small hockey puck. The guy was really heavy. So when this hits him, it's not going to move him back that much, okay? Like, what if we change this to, let's say, another person, right? Or like this example that we went, these two objects, and yeah, that they're going to be moving a little bit faster, right? Depending on the size. So that's what these formulas tell us, okay? They tell us how fast objects are going to move when they collide. Okay? Okay, let's do another example. So this is on the, what side is this on? Left side. So here we have a bullet. Let's make this the bullet. We know how much it weighs, 0.035. So M1, I'm going to do that over here too, 0.035. Might as well, right? Fill in what you can. Strikes a 5 kilogram stationary piece of wood. So let's say it's just a piece of wood. And we know it weighs 5. So if M2 is 5 here, M2 is 5 here. Okay. The piece of lumber and the bullet fly together at 8.6 meters per second. Okay, so here the bullet is obviously going to crash into a piece of wood that's not moving. Once, let's put right here, they collide. Let's add some fire on it. There we go. It's got to have some yellow in it too, right? Okay, so once they collide, you're going to have the piece of wood and the bullet embedded in there. And the piece of wood is going to be moving now, right? Because the bullet made it move. So we know how fast. It says here, that's why you have to read these problems, because you have to see, you have to plug in the numbers in the correct spot. So here it says the piece of lumber and the bullet fly together 8.6 meters per second. So that actually goes over here. It goes right here. 8.6. They're both moving, right? So what is the speed of the bullet before it struck the lumber? So notice the piece of lumber wasn't moving, right? It was stationary. So we know the velocity of that guy right there, 0. So now we are trying to solve V over here, okay? So how do we solve for V over here? Well, break it down one step at a time. 0.035 V. 5 times 0 is 0. That's nice, right? 0.035 plus 5 is 5.035. We have to multiply these two numbers because that's what the problem is telling you to do. 5.035 times 8.6, 43, I'm just going to say 43.3. So remember, we are solving for V, this, right there. So now what do we do? To isolate V, you have to do this, right? This cancels and we're left with V equals 43.3, 43.3 divided by 0.035, and that gives me 1237. Okay. Does that make sense? Yes, it should, right? I mean, the velocity of the bullet is really fast. This is 1,000. It's not a comma. It's not a period. It's a comma. So 1,237 meters per second. So we can figure out with this formula, if you have two objects, if one is not moving, if they're both moving, if, you know, like once this gets embedded in the piece of lumber and they're both moving, okay? This is assuming that the, well, yeah, once the bullet gets embedded and they're both moving, we can figure out the mass of an object, how fast something's going, and so on, okay? So there we go. Okay, now we're going to go into elastic. So In elastic equation, this is the formula for what's called an elastic equation, okay? The other equations were inelastic. Inelastic is when they both collide and they move together. Elastic, picture like a rubber band, right? You get a rubber band between your fingers and you pull it, it's going to kind of go back to its original spot, right? So picture elastic equations kind of like that. This is where when objects collide and they don't stick together, okay? So usually in car crashes, when you have two objects that are going to collide with each other, they're going to stick together, right? And they're going to start moving. But what if they don't? So that's an elastic equation, okay? So like if you're playing pool and you hit a billiard ball and it hits the other one, they're going to ricochet off each other, right? So here's the formula. Very similar, right? The only thing that's different is the M1 plus M2 times V both, right? Okay, so here we have our first example. Each croquet ball has a mass of 0.900 kilograms. Ball A, so we're going to label this as ball A and ball B. Okay, let's label them. So we know that they all have the same mass because it says each one. So it's okay to put, for all the M's, we can put the mass. Okay, ball A travels 20 meters per second. So we know ball A is going 20 meters per second. And it strikes ball B, which is at rest. So this guy here is at rest, ball B. You have one ball here, it's moving. The other ball is not moving. There's a collision here. Assume the balls slide on a frictionless surface and all the collisions are head-on. What is the speed of ball B if A stops moving? So if this guy here stops moving, but it transferred its energy to ball B, so this ball hits this one, and then A stops, but then B starts moving. I'm sure you guys have seen that in pool, right? Where somebody hits a ball, and then that original ball stops moving, but it makes the other ball move, right? So we're gonna figure out how fast they are going. So we know here, assume that, okay, what is the speed of B if A stops moving? So we know A, this guy right here, is gonna stop moving. And now we wanna find out this one right here, V. Right? So we do what the problem tells you, 0.9 times 20. 0.9 times 20, that gives me 18. 0.9 times 0, 0. 0.9 times 0 is 0. And now to solve for V, we're going to divide. V ends up being 18 divided by 0.9. 18 divided by 0.9. And that gives me 20. So it transferred all its energy. Okay. Let's do another example. So here, let's say it's the same thing, same like a billiard ball or a croquet ball or so on. So here it says that you have two of them, and we're going to label it A and B. Sometimes it might say like car, you know, well, not car, it might say like object, red object and blue object, you know, as long as you label them, you should be okay. So here we know that each one has the same mass. That's not always going to be the case. I mean, just do whatever the problem is telling you and you should do fine, okay? And that's a plus right there, equals. Okay, so, and you know what, let's put these guys in parentheses so that they can be separated. Now we know that ball A, we know how fast it's going. Okay. Ball A is going this fast, velocity, right, 5. Ball B is at rest, so the velocity of B is 0. Assume that they slide on a frictionless surface. What is the speed of B? So we want to know the speed of this one if A continues moving. So if A continues moving at 3. So here you have this ball and it's moving, right? A. This one is not moving. It collides. Collision, boom, right there. So now the problem is saying, what is the speed of B if A is moving at 3? So here, both of them are going to be moving, right? But maybe this one, you know what, let's draw a little. So here, after they collide, right here, let's say this one starts moving that way, and this one starts moving that way, right? Because it collided, and then this one went that way, and then this one went that way, okay? So we set up everything here. Now it's just working out each little problem at a time. So we're going to do 0.2 times 5, 0.2 times 5, 1. 0.2 times 0 is 0. 0.2 times 3 is 3. That's not right, is it? 0.2 times 3 is 0.6. 0.6. And we have 0.2v. Okay. So what we're going to do is this. We're going to move it to the other side, but we're not going to divide because here we have plus, right? We're going to combine kind of like terms, right? So 0.6 plus 0.2. So this, to move it to the other side, you need to subtract, right? You need to do the opposite. So 1 minus 0.6, 1 minus 0.6 gives me 0.4 equals 0.2v. So now 0.2 times v, right, this is multiplying. Now you can do the opposite here, which is divide. That guy cancels, and we're left with 0.4 divided by 0.2, and that gives me 2. Okay. So there we go. We were able to figure out how fast this one was going, right? We know how fast this one was going. We know that the mass was 0.2 and it was going 5 meters per second. It struck this one, which wasn't moving at all. After the little collision here, this one, the problem told us that A was continuing to move, right? It was moving at 3 meters per second. This one was moving 3 meters per second. And we wanted to find out how fast this one was moving, and we found it. Just 2. And there we go. That's pretty much it. So just to give you a quick little review of the 2 formulas that we went over. Here we have inelastic equations, and this is when objects collide and stick together. Whether you have 2 cars that crash into each other and they both start moving, or you have like a bullet that hits a piece of wood and it's lodged in the wood, and then they both start flying, right? So that is the inelastic, and that's this part right here, m1 plus m2, right? And velocity, well, they're both moving. Okay, that's called an inelastic equation. The elastic is when objects don't stick together. And this is when you have like 2 billiard balls that collide with each other, and they're not going to stick with each other. They're going to kind of bounce off each other. Okay, but there you go. Those are the 2 formulas for inelastic and elastic equations.